Unit 9, Test Review, Newton's second law of motion. When we look at our review packet, the first thing we should notice up along the top is that we've got the equations that we'll see on our test. So first we've got F equals ma, so that's our force equals our mass times our acceleration. We've got Fg equals mg, that means our force due to gravity equals the mass times the acceleration due to gravity. We've got our normal force equals our gravitational force. And again, remember that the gravitational force always acts in the downward direction. The normal force is the same, but in the opposite direction. The next equation we have is our force due to friction, which is going to be your coefficient of friction, or your mu value, times the normal force, or the force due to gravity. And then the last thing you have there are three acceleration due to gravity constants. So the acceleration due to gravity on the moon is 1.6 meters per second squared. The acceleration due to gravity on Mars is 3.8 meters per second squared. And the acceleration due to gravity on Titan is 1.35 meters per second squared. You will see all of that on your test tomorrow. Now let's look at the questions. Question number 1 says, what causes objects to accelerate? And it's a force that causes acceleration in an object. Number 2 says, for a constant force, what happens to the acceleration of an object if its mass increases? So let's look at the equation F equals ma. If our force on the left-hand side of that equation is held constant, and the mass goes up, the acceleration is going to have to go down. So imagine this. Let's say that our force is a constant, but our mass is multiplied by 2. In order to keep the force the same, our acceleration would have to be divided by 2. Mass and acceleration are inversely related. If we look at number 3, it says describe the type of relationship between acceleration of an object and the net force acting on it. So we look at that F equals ma equation again, and this time our force and our acceleration are on opposite sides of the equation. So that means if we increase the force on the left-hand side of the equation, the acceleration is going to have to increase on the right-hand side of the equation to keep both sides equal to each other. Force and acceleration are directly related. Okay, question number 4 says, how does the direction of an object's acceleration compare to the direction of the net force acting on it? So if we're applying a force to an object, it's going to cause the object to accelerate in the same direction as the force. So the acceleration will be in the same direction as the net force. Number 5 says, strange as it may seem, it is just as hard to push a car on the moon as it is to push the same car on the Earth. This is because, and our answer would be A, the mass of the car is independent of gravity. So again, we've got F equals ma. Okay, the force or the push on the car is going to be dependent on the mass, but not dependent on the gravity. Number 6 says, given a graph of y versus x, describe how you could tell if y is directly proportional to x. And this is like the graphs that we did in this chapter and in previous chapters. So if we draw a real simple graph, we've got y on our vertical axis, we've got x on our horizontal axis. If we're looking at a relationship that's a direct proportional relationship, we're going to see a straight line that has a positive slope. Like when we were looking at our velocity versus time graphs for a constant acceleration. For number 7, if the net force acting on a cart doubles, what happens to the cart's acceleration? So again, what we can look at is our F equals ma equation. Force is on the left-hand side of the equation. Acceleration is on the right-hand side of the equation. So that means force and acceleration are directly proportional. Whatever we do to our force is going to have the same effect on our acceleration. So doubling our force would double our acceleration. Looking at number 8, suppose a force is causing a cart to accelerate. If suddenly a load is dumped into the cart so that the cart's mass doubles, what will happen to the acceleration? Well, this time mass and acceleration are on the same side of the equation. If our force on the left-hand side is held constant, mass and acceleration are inversely related. So if we were to double the mass, we would have to cut the acceleration in half. Number 9 says the graph that best represents the relationship y equals kx, where k is a constant, is, so if we look at that particular equation, y and x are on opposite sides of the equation. That means they're directly proportional. If you were to increase y, that would increase x. If you were to decrease y, that would decrease x. So graph B would represent that direct proportional relationship. Number 10 says a horizontal force of 100 newtons is required to push a cart across a factory floor at a constant speed. What is the net force on the crate, and what is the force of friction on the crate? The key to this question is constant speed. Remember that if an object is moving at a constant speed, its acceleration is 0. So if we look at our F equals ma equation, if the acceleration is 0, that means the net force on that object must be 0. Then to calculate the force of friction, we know that the applied force minus the friction force equals our net force. So we would take 100 minus, that should say 100, equals 0, so our friction force is 100 newtons. Okay, so for that, our net force will be 0, our friction force will be 100, and if we take the 100 newtons for applied force and subtract the 100 newtons for the friction force, that's where our net force will be 0, which means that our acceleration will be 0, which means the constant speed of our object. Number 11 says, what is the cause of friction and in what direction does it act with respect to the motion of a sliding object? So friction is caused when two objects are in contact with each other, and they're always going to be in opposite directions from each other. And that's the reason why when we calculate the net force, we take the applied force and we subtract the friction force, because the two forces are in opposing directions, and we know that we subtract when we've got vectors in opposite directions. Number 12 says friction acts on a material that are in contact with each other and always acts in the direction to oppose motion. And that came right from the reading in the textbook. Number 13 says the force of friction between the surfaces depends on the materials that are in contact and how much the surfaces are pressed together. Number 14 says air resistance, which is a friction acting on something moving through the air, is very common form of a liquid friction. For number 15, we're looking at another graph. Okay, this is a specific graph this time. It has velocity in meters per second on the y-axis, and it's got time in seconds along the x-axis. And when we look at the relationship between velocity and time on this graph, it's a direct relationship. As our velocity is going up, our time is also going up. So when we look at the choices there, V is directly proportional to T would be choice D. Looking at the math problems, for number 1, we're trying to calculate force. So force equals mass times acceleration. So we've got 3,000 kilograms times 4 meters per second squared. So our force is 12,000 newtons. For number 2, this time we're trying to calculate mass. So our mass is going to equal our force divided by our acceleration. So 13 newtons divided by 90 meters per second squared will give us a mass of 0.14 kilograms. And for number 3, an astronaut is standing on one of Saturn's moons, Titan. How much would an astronaut on Titan weigh if his mass was 55 kilograms? Whenever you see weight, you want to use Fg equals mg, because your force due to gravity is equal to your weight. So we've got 55 kilograms times 1.35 meters per second squared is going to give us a force due to gravity, or a weight, of 74.25 newtons. For number 4, on the planet X, a 10 kilogram object weighs 75 newtons. What is the acceleration due to gravity on X? So we're trying to calculate G. G equals Fg over m. So we've got 75 newtons divided by 10 kilograms gives us an acceleration due to gravity of 7.5 meters per second squared. For number 5, on Mars, an astronaut weighs 250 newtons. What is the mass of the astronaut? So mass equals our force due to gravity, or our weight, divided by acceleration. So 250 newtons divided by 3.8 meters per second squared gives us a mass of 65.8 kilograms. For number 6, a 1.5 kilogram book is pushed across a table with an acceleration of 0.25 meters per second squared. What is the net force? So force equals mass times acceleration. Our mass is 1.5 kilograms. Our acceleration is 0.25 meters per second squared. So the force is 0.375 newtons. Number 7 says on the launch pad, a rocket has a mass of 1 million kilograms. In order to lift off, its engines must produce a combined thrust of 12 million newtons. What is the initial acceleration of the rocket? So we're going to take our acceleration equals force divided by our mass. So we've got 12 million divided by 1 million. So our acceleration is going to be 12 meters per second squared. For number 8, what is the mass of a box that weighs 500 newtons? So mass equals the force divided by the acceleration. 500 newtons divided by 10 meters per second squared is going to give us a mass of 50 kilograms. Number 9, what is the force of friction acting on a 500 Newton sled if the coefficient of friction between the sled and the floor is 0.33? So our force due to friction is going to equal our coefficient of friction times the normal force, or the force due to gravity. So we've got 0.33 times 500 newtons gives us 165 newtons for our friction force. For number 10, what is the force of friction acting on a 67 kilogram box if the coefficient of friction between the box and the floor is 0.26? So our normal force equals our force due to gravity, which equals our mass times our acceleration due to gravity. So 67 kilograms times 10 meters per second squared is going to give us a normal force, or a force due to gravity, of 670 newtons. Our friction force equals mu times our normal force, so 0.26 times 670 newtons is going to give us a friction force of 174.2 newtons. Problem number 11 will be finished on the next video.